My name is Holden Lee, and I will talk about estimating normalizing constants for log-concave distributions, algorithms, and lower bounds. This is joint work with Rong Ge and Jianfeng Liu. We consider the following problem. We are given gradient access to a function f from r to the d to r. Suppose that f is L smooth and mu strongly convex, and let kappa equals L over mu be the condition number. We will implicitly assume throughout that f is twice continuously differentiable, so this means a lower and upper bound on the Hessian of f. Our goal is to estimate the normalizing constant. Z equals the integral of e to the minus f of x over r to the d within a multiplicative factor of 1 plus or minus epsilon with probability greater than or equal to 3/4. This is the normalizing constant of the probability distribution that is proportional to e to the minus f of x. Because f is convex, we say that this distribution is log concave. Note that this probability, 3/4, can be amplified by running the algorithm multiple times and taking the median. We measure the complexity of this algorithm by the number of queries to the gradient. Note that for all our algorithms, the running time will be comparable to the query complexity. The motivation for this problem comes from TCS, Bayesian machine learning, and statistical mechanics. This is related to the classical TCS problem of estimating the volume of a convex body, because the uniform distribution over a convex body is a degenerate log concave distribution. In machine learning, computing the normalizing constant of a posterior distribution is a fundamental task, used, for example, in Bayesian model selection. Finally, in statistical mechanics, Z is referred to as the partition function and also related to the free energy. We give both an upper and lower bound for this problem. For this talk, I'll assume kappa as a constant and focus on the dependence on d and epsilon. For the upper bound, we design an algorithm based on annealing, multi-level Monte Carlo, and UOD-RMM under damped Langevin dynamics with the randomized midpoint method that solves the problem with d to the 4/3 over epsilon squared queries. For the lower bound, we show that for constant condition number, any algorithm requires d over epsilon squared queries in the limit as epsilon approaches 0 and d approaches infinity. The previous best upper bound had a d cubed dependence or a d to the 4th dependence with no dependence on kappa given function queries. This algorithm by Lovash and Vempala also applies to calculating the volume of a convex body. This is the first non-trivial lower bound for strongly convex f in the sense of having a dependence on dimension. I'll go over each of these three ingredients for the upper bound, focusing on the beautiful idea of multi-level Monte Carlo, which originated from the statistic literature and is key to getting this upper bound. If you only take away one thing from the talk, this is a good choice. Upper bound. Here are the three ingredients for proving the upper bound. The first is annealing, which reduces the problem to calculating the expected value of a function gi over a bunch of intermediate distributions. The second and key ingredient is multi-level Monte Carlo, which allows efficient estimation of this expected value given a sampling algorithm that can be coupled at different discretization levels. Finally, we combine this with a state-of-the-art sampling algorithm, UOD-RMM, recently proposed by Ruoxi Shen and Yuntat Li. None of these ingredients are new, but as far as we know, this is the first time that multi-level Monte Carlo has been used in theoretical computer science. The first ingredient is annealing. We define intermediate distributions by adding a quadratic to f, i.e., multiplying p by a Gaussian. We start with low temperature, that is, a narrow distribution P1, whose normalizing constant Z1 we can estimate by the normalizing constant of the Gaussian, and gradually anneal to Pn plus 1 equals P. We reduce the counting or integration problem to a sampling problem as follows. Write Z as a product of ratios Zi plus 1 over Zi. Each ratio can be written as the integral of a function gi over a distribution pi, i.e. an expected value. We can estimate this by sampling from the distribution pi using a Markov chain Monte Carlo algorithm and taking an average. We need square root d levels, where the temperature increases by factors of 1 plus 1 over square root d, so that the variance of each gi is a constant. We can't estimate g with just one jump because then the variance is exponential. The second ingredient is multi-level Monte Carlo, which gives us an efficient way to estimate the expected value of gi under pi, given that we can approximate sample from pi by discretizing a continuous stochastic process and couple the process at different discretizations. There are standard algorithms for sampling based on Langevin dynamics, which I'll explain later in this talk. For now, let's assume we have such a sampling algorithm and see what to do with it. Before I explain multi-level Monte Carlo, let's review regular Monte Carlo. Our goal is to estimate the expected value of g of x, where in our case, g is the output of some continuous stochastic process. In regular Monte Carlo, we obtain a lot of samples at a fine discretization, eta, and take an average. There are two costs we have to multiply: the cost of discretization to get a single sample, and the number of samples that we need. Now, multi-level Monte Carlo, introduced by Michael Gauss in 2008 and popular in the statistic literature, is a generic way to improve rates for estimating the expected value of a random variable y, given biased estimates y eta, provided the following conditions hold. As eta approaches 0, the estimate becomes unbiased, the cost to sample y eta increases, and importantly, there exists a coupling of random variables y eta over 2 and y eta such that the variance of their difference goes to 0. In particular, this variance is much smaller than the variance of y. In our case, y equals g of x, where x is the output of a continuous stochastic process. And our biased estimates are g of x eta, where x eta is the discretization with step size eta. For the first condition to hold, it is sufficient for x eta to approach x in Wasserstein distance, and for the function g to be Lipschitz. For the third condition to hold, it suffices to find a coupling so that x eta over 2 minus x eta approaches 0. Here's the idea between multi-level Monte Carlo. In regular Monte Carlo, since the samples have large variance, we need to take a large number of samples. And we have to use the finest discretization for all the samples, so the cost per sample is large. In multi-level Monte Carlo, we write g at the finest discretization, say eta 2, as the sum of g at the coarsest discretization, say at eta 0, plus a telescoping sum of correction terms, g at finer discretizations minus g at coarser discretizations. At the coarsest discretization, eta 0, the variance is still large, so we have to take a large number of samples. However, this is offset by the small cost per sample. At the finer discretizations, the variance of this difference, and hence the number of samples that we will need, is small because of the way we couple the random variables, which offsets the large cost per sample. Indeed, you can see that the variance at eta 0 is large as before, but the difference between the coupled processes for eta 1 and eta 0 is small. And at the finest discretization, it's even smaller, almost imperceptible. To get the total complexity, we multiply the number of samples with the cost per sample at each level, which is never too large, and add them up. We can work out the optimal number of samples to take at each level. It will decrease geometrically and be at least 1. Now let's formalize this picture. To estimate the expected value of g of x, where x is the output of a continuous stochastic process, instead of sampling g of x eta k at the finest discretization directly, we take a bunch of intermediate discretizations, eta 0 through eta k, where each is half the size of the previous. We consider g at the coarsest discretization, eta 0, which has a large bias, and then correct this with a telescoping sum of g at finer and finer discretizations, g of x eta j minus g of x eta j minus 1. We estimate the expected value by estimating the expected value of each summand separately using samples. The advantage of doing this is that the coarse discretization is much cheaper to compute, and that for finer discretization, these differences estimated using coupling have much smaller variance, so require much fewer samples. Later, I will explain how we do this coupling. The final ingredient for the upper bound is the sampling algorithm, Langevin dynamics, which gives us a way to sample from a distribution proportional to e to the minus f of x, given access to gradients of f. Overdamped Langevin dynamics is essentially gradient flow plus Brownian motion, and underdamped Langevin dynamics incorporates momentum and can be seen as an accelerated version. The important fact about Langevin dynamics is that it has fast mixing to the stationary distribution, e to the minus f, when f is convex, that is, when the distribution is log concave. To get an algorithm out of this, we have to discretize this continuous process. Discretization of Langevin dynamics has been well studied in recent years. Relevant to us will be convergence to the stationary distribution e to the minus f in TV distance, and particularly in Wasserstein distance. This table shows the number of steps needed to converge within distance epsilon for several different discretization algorithms. We'll be using these results as a black box. Recall that to use multi-level Monte Carlo, we not only need a sampling algorithm, we also need a way to couple it at different discretizations, eta and eta over 2, such that the distance between x eta over 2 and x eta goes to 0 as eta goes to 0. For simplicity, I'll illustrate the coupling for overdamped Langevin dynamics with the Euler-Murayama discretization. But a similar procedure works for underdamped Langevin dynamics and other discretization schemes. We start with the continuous process. When discretized, this becomes gradient descent plus Gaussian noise. To couple the discretization with step size eta over 2 and eta, we let the Gaussian in the eta discretization be the sum of the Gaussians in the two half steps. One way to think about this is that we're taking one realization of this continuous process with the randomness fixed, and then discretizing at step sizes eta and eta over 2. Then we must have a relationship between the noise terms in these two discretizations. By the way we constructed the coupling, the square distance between x eta over 2 and x eta is comparable to the square distance between x eta in the continuous process, which approaches 0 as required. The same idea can be used for more complicated discretizations, but we may have to generate correlated rather than independent Gaussians. We're now ready to make everything quantitative, to quantify how many queries we need for multi-level Monte Carlo and plug in the guarantees for the Langevin-based algorithms. This theorem gives the number of queries we will need to estimate the expected value of G with bias at most epsilon b and variance at most epsilon sigma squared. Note it's important for our application to have the freedom to choose different epsilon b and epsilon sigma. Suppose that the following hold. There's a coupling so that this difference x eta over 2 minus x eta decreases quickly enough as eta goes to 0, faster than 1 over eta, or faster than eta. The coarsest discretization is reasonable, and the finest discretization is small enough to make this bias smaller than epsilon b. Then the cost is dominated by the number of queries is dominated by two things. Reducing the variance at the coarsest level to epsilon sigma squared, which is 1 over quantity epsilon sigma squared times eta 0, and the cost of the finest discretization, which is 1 over eta k. Now for regular Monte Carlo, we have to reduce the variance to epsilon sigma squared at the finest discretization. So we get a term 1 over epsilon sigma squared times eta k, which is larger. Now, for our annealing procedure to work, we need the bias to be epsilon over square root d, and the variance to be epsilon squared over square root d. This is so that adding together the errors from the different temperatures, we get something on the order of epsilon. Plugging into the guarantee of the ULD-RMM algorithm and calculating what eta 0 and eta k need to be, we get that d to the 5/6 over epsilon squared queries are needed for each temperature. Finally, multiplying this by the number of levels, square root d, gives us the final bound, which is d to the 4/3 over epsilon squared. This is the upper bound that we prove. In this table, we compare the guarantees we can get using regular and multi-level Monte Carlo. The best upper bound we can get using regular Monte Carlo, using MALA, Metropolis Adjusted Langevin algorithm, is d squared over epsilon squared. Note that regular Monte Carlo is unable to take advantage of the better guarantees in Wasserstein distance given by underdamped Langevin dynamics and ULD-RMM. In fact, they give strictly worse bounds for estimating z. This is because of the worse dependence on epsilon than in MALA. In contrast, multi-level Monte Carlo does just fine. Finally, we note that an improved bound for sampling will give an improved bound for estimating z. If we were able to get Wasserstein distance, epsilon, with order of d to the gamma steps, then we can estimate z with order d to the 1 plus gamma steps. Our second main result is the lower bound. Recall that we are estimating the normalizing constant in d dimensions with a multiplicative error of 1 plus or minus epsilon. Let's assume the condition number is a constant. we show that the lower bound is d over epsilon squared in the limit. There are two main steps. First, we show a lower bound in low dimensions by reduction to the problem of distinguishing biased coins. Second, we get a lower bound for high dimensions by taking a product distribution. Note that it is necessary that d be large here. Better dependence on epsilon is possible when d is less than or equal to 3 by deterministic quadrature methods. First, we show the lower bound for low dimensions, i.e., without a multiplicative dependence on dimension. We show that any algorithm for k dimensions must make at least 1 over epsilon to the 2 minus big O of 1 over k queries. The proof idea is as follows. We will try to distinguish between two families of distributions. We let f of x equal to the quadratic x squared over 2 plus a random function from one of the two families. To define these functions, we split up a cube of side length 1 over square root k into n cubes or cells. We let each cell either be type 1, the 0 function, or type 2, a bump function that is 0 on the boundary. In the first family, we let each square be type 1 with probability 1/2 plus delta. And in the second family, we let each square be type 2 with probability 1/2 plus delta. I.e., we're flipping biased coins with probability 1/2 plus delta and 1/2 minus delta in the two cases. The idea is that the normalizing constants for these two cases differ significantly, but it is hard to tell these distributions apart with few queries. The core lemma is that to distinguish with constant probability, say 3/4, whether a biased coin has probability 1/2 plus delta or 1/2 minus delta of landing heads, an algorithm must take 1 over delta squared samples. The intuition is that if the sample size is 1 over delta squared, sample size is n, then the margin of error for the estimated probability is 1 over square root n. So we need n to be at least 1 over delta squared in order to get the margin of error less than delta. We can define our function in such a way that the normalizing constant is the normalizing constant of the Gaussian minus a constant times the proportion of type 2 cells. These were the ones that are the bump function rather than the 0 function. Note there is a factor of L squared, where L is the side length of the cell, which we'll ignore in this calculation. Thus, to estimate z within approximately 1 plus delta, we need to estimate the number of type 2 cells within 1 plus delta, i.e. distinguish whether we were in the first case or the second case. Each query gives us information about one cell, which is like information about one coin flip. Thus, this reduces to the question of distinguishing coins with bias 1 plus or minus delta, which requires 1 over delta squared samples. The second step is to obtain a lower bound for high dimensions. We take a product distribution, partition the d dimensions into d over k groups of size k, and use the low dimensional construction for each of these groups. Let f be the sum of functions fi on k coordinates. The fi are either all drawn IID from case 1 or all drawn IID from case 2, and we have to distinguish between these two cases. Roughly, to get accuracy 1 plus or minus epsilon for f requires getting accuracy 1 plus or minus epsilon k over d for some fi. And one query of f gives us information about up to d over k FIs. Working through this reduction, we can get an extra factor of d in our lower bound. To conclude, we've shown that the number of queries is lower bounded by d over epsilon squared and upper bounded by d to the 4/3 over epsilon squared. The biggest open question is to close this gap. In the lower bound, we focused on the dependence on d, but it would also be good to understand the dependence on kappa. Another interesting model is where we only get stochastic queries, such as stochastic gradients. Our initial motivation was to get upper and lower bounds for sampling. Using annealing plus multi-level Monte Carlo, an algorithm for sampling gives an algorithm for estimating z using d times as many queries. We've been unable to give a lower bound for sampling with exact gradient evaluations with dependence on d, and this is a big open problem. Another interesting direction is to consider the distributions restricted to convex sets. Perhaps these techniques to give better algorithms for volume estimation of convex sets. Finally, it will be great to find more applications of multi-level Monte Carlo. Thank you for your attention.